We've defined radioactivity as a spontaneous process, a natural process, a random process in which a nucleus breaks apart. It's not stable. For whatever reason, the nucleus is not stable, and as a result of that instability, it breaks apart into something else. Now, there are four types of ionizing radiation that we talk about, at least, that can be released as a result of this radioactive decay. When a nucleus such as carbon-14 decays, it will produce another nucleus like nitrogen-14 and then some ionizing radiation. The four types of ionizing radiation that we look at in physics 30 are called alpha, beta negative, beta positive, and gamma. All four of these will ionize matter, which means all four of these will cause atoms to turn into ions, which can lead to all kinds of issues, right? Chemical reactions that aren't supposed to take place, and then it can lead to, in us, sickness and all kinds of varying degrees. We're going to talk today about those four types of ionizing radiation that are released as a result of radioactive decay, starting with alpha particles. First couple are already a review for you. I realize that, but we're going to go through those again. When an alpha particle is released, what really happens is that this nucleus that is big and unstable breaks apart, releasing a small chunk of a nucleus. In other words, 2 protons, 2 neutrons off of it. Now, that still leaves a fairly big nucleus left over. It's not that we're concerned about right now. It's the alpha particle that's been released, the ionizing radiation that's released, that we want to focus on right now. What's the same thing as an alpha particle? You know what? I shouldn't say that. That's a bad way to say it. What's the same thing? What's another term for an alpha particle? Yeah, it's not just the same thing. It is the same thing. Like, it's a helium nucleus is an alpha particle, or an alpha particle is a helium nucleus. We got 2 protons, we got 2 neutrons. That's a helium nucleus. That's an alpha particle. It's exactly the same thing. And of course, since it's a helium nucleus with protons and neutrons, it is matter. Matter is anything with mass, and this, because it has protons and neutrons, is matter. What's the cause of it? What's the cause of it? You might remember on Friday we talked about 3 forces in the nucleus, 2 of which were relevant to the discussion that we're having with alpha particles here today. One was called the electrostatic force, and that's not a new force. We know that force, we've known this since back in February. We've known that this force can be attractive or repulsive, but in the nucleus it can only be repulsive. Why? Well, don't protons attract neutrons? They don't, actually. Protons attract neutral objects, but protons won't attract neutrons because you don't have a separation of charge produced in the neutron. So protons don't attract neutrons. Protons don't attract anything electrically in the nucleus, but they do repel each other. So there's a force of repulsion caused by that electrostatic force. There is also a force of attraction in the nucleus acting between everything: protons, neutrons, protons and neutrons. If we have too many protons, and that tends to occur in really big elements, if we have too many protons relative to the number of neutrons, then the electrostatic repulsive force ends up being bigger than the strong nuclear attractive force. And if the repulsive force wins out over the attractive force, then the nucleus isn't stable. It breaks apart and releases an alpha particle in an attempt to become more stable. Now, beta-negative decay works on a completely different principle. It's still ionizing radiation that's released as a result of a nucleus being unstable, but it's unstable for a different reason. Firstly, a beta particle would have properties that look like this. 0 minus 1 beta, in other words, 0 minus 1. It's another term for beta particle. Yeah, it's an electron. And that's matter, of course. Much, much smaller matter, but it still has mass, so it's matter. The cause of it is because we have too many neutrons. But it's not a force thing. Too many neutrons doesn't cause you to have too much of a certain force that makes it break apart. In fact, too many neutrons would actually give me a stronger attractive force. So by the force argument, it should be really, really stable. But the problem is energetically, it's not. It's energetically unstable. And as a result of that unstable energy, the nucleus does something to make it more stable. The nucleus will change a neutron. You got too many of them, remember? So it changes a neutron into a proton. That improves the ratio, right? Less neutrons, more protons. Give you a little hint as to what comes next. A proton and an electron. You got to have that electron there. How come? If you didn't have that electron there, you'd violate a pretty fundamental law. Which one is it? Yeah, you don't have this electron, then you've got neutral has become positive, and that just can't happen. Neutral stays neutral. It's just different neutral, that's all. Okay, this electron is what gets fired off as the beta particle. It doesn't belong in the nucleus, so it gets fired away. Beta plus decay. Beta plus particles look like this, 0 plus 1 beta. And another name for a 0 plus 1 particle would be an anti-electron. This isn't matter, this is antimatter. And the antiparticle of an electron is called, you could call it an anti-electron, I suppose, but usually we would call it a positron. And positron emission or beta plus decay occur once again when you have too many protons. But this time, it's not an issue of the force of repulsion being too big. This time, it's an issue, once again, of the energy being unstable. So, what does the nucleus do? Tries to reduce the number of protons. And it does that by changing a proton into a neutron. And what else? Yep, Philip. A positron. E plus, a positron. And of course, the positron doesn't stay in the nucleus. It gets kicked out. That was your beta plus particle, your positron that was produced there. Now, this one's new to you. We didn't go over this on Friday. Gamma decay. A gamma ray has this notation, 0, 0, gamma. That means that a gamma particle has how many protons? 0. How many neutrons? 0. How many electrons? 0. How many positrons? 0. What is this? Matter or energy? Energy. Specifically, we would say that it is electromagnetic radiation. You guys remember way back at the very beginning of your EMR unit, we talked about the 7 types of EMR and how each of them were produced. Radio waves are produced by oscillating charge. Visible light was transitions of electrons in the atom. Gamma rays were nuclear decay. This is what we're talking about, right? Nuclear decay. Gamma ray photons are produced as a result of nuclear decay. Now, what's the mechanism or why are they produced? They're produced as a result of a number of other processes, including alpha and beta decay. The nucleus is sometimes left in an excited state after something has happened, like alpha or beta decay. But it doesn't want to be there. So as it goes back down to its normal state, it gives off a photon, a gamma ray photon. Alpha decay has just occurred. The nucleus is excited, but it goes back to normal, giving off a gamma ray photon. Beta decay has just occurred. The nucleus is excited, but it doesn't want to be there. So it goes back down to its normal state, giving off a photon, a gamma ray photon in the process. Nuclear fission has just occurred, or some other kind of nuclear reaction has just occurred. The nucleus is left excited. It goes back to its normal state by giving off a gamma ray photon. So this is kind of like a byproduct, in a sense, of something else happening. It doesn't happen without something else happening first, leaving the nucleus in an excited state. All right, I want to talk about two properties of each of these types of ionizing radiation. Firstly, the penetrating power, the ability of these types of ionizing radiation to penetrate or go through matter, and the ionizing power or ionizing potential, the ability to turn atoms into ions. Alpha particles have a very low ability to penetrate matter. They can probably be stopped by a couple of sheets of paper. Somebody gets mad at me one day, decides they're going to take out their frustration on me. They bring in their alpha particle gun, and they bring it into my classroom, and I say, bring it on. All I got to do is hold up a couple pieces of paper just like that to shield myself from your fancy alpha particle gun. Literally a couple sheets of paper. Literally my clothes would shield me from alpha particles. Now, why do alpha particles have such a low ability to penetrate matter? Well, it's because they have such a high, in quotation marks, charge and mass. Why do I put high in quotation marks? Yeah. Good. Perfect. It's not really that high, right? Like the mass of an alpha particle is 10 to the minus 27 kilograms. But compared to the mass of a beta particle, which is 10 to the minus 31, it's really, really high. The charge isn't all that high, right? It's plus 2. But compared to the charge of a beta particle, which is minus 1, it's twice as much, right? So because of the relatively high charge and mass, the penetrating power ends up being pretty small. Now, beta particles, whether you're talking about beta negative or beta positive, beta particles have a lower charge and a lower mass. So we would expect the penetrating power to be higher, right? The penetrating power we say is moderate. A couple centimeters of flesh. So beta particles would actually go into your skin. They'd actually penetrate the outer layer of your skin into flesh, 1 or 2 centimeters. They wouldn't penetrate into internal organs, but they would certainly go further than alpha particles would. Listen, it's not so much being bombarded by alpha particles or beta particles that we would have to worry about in terms of radioactive exposure. It would be more consuming something that was radioactive and then having it decay once inside my body that would be the issue. Maybe I happen to live near Chernobyl and I'm consuming some kind of plant that was grown in soil that was contaminated by radioactive material. I literally am eating radioactive plants. Then they decay once they're in my body. It's not ones that have already decayed that's so much the problem, because they can't really get inside my body, right? The penetrating power is too low. Okay, gamma rays. Gamma rays have no charge. They have no mass. What do you think their penetrating power is? Yeah? Sorry? Yeah, we wouldn't want to say everything, but it's very high. Very high, like several centimeters of lead. Years ago, I went to a professional development session at the Tom Baker Cancer Clinic in Calgary, and they were telling us all about radiation therapy and how they do it and what kind it is and where it comes from and so on. And they took us on a tour, and one of the places they took us was a room where they do radiation therapy on cancer patients. in this room. I forget what the number was, but they said that it was the walls of this room were a few feet thick, made out of concrete. Why would they be so thick? And why are they made out of concrete? Like the walls in my house are made out of 2x4s, wood, hollow in the middle. Not the 2x4s, but the walls. Why would the walls be so thick, and why would they be made out of concrete? Sorry? Yeah, because they use gamma rays. You gotta hate to be, listen, if they make that room out of 2x4s, like my house is, you gotta hate to be the guy that has his office next door. They make them out of a few feet of concrete so that they shield the outside from, we'll call them rogue gamma rays, so that you don't get struck by gamma rays that are just flying around. Okay, let's talk about the ionizing potential of them now. The ability of these things to ionize matter. Alpha particles have a very low ability to penetrate matter, but because they stop so quickly, because they have a low ability to penetrate matter, their energy gets dissipated very quickly and therefore has a high ability to ionize matter. Beta particles, they're kind of the fence sitters. They can't decide whether they want to penetrate matter very well. They're kind of in the middle. They can't decide whether they want to ionize atoms very well. They're kind of in the middle. They have a moderate ability to ionize matter. And gamma rays, although gamma rays have a very, very high penetrating power, their ability to ionize matter, I don't want to say it's low, but we will say it's relatively low compared to the others. So why is it that we'd use gamma rays in the treatment of cancer as opposed to alpha particles? If alpha particles can ionize matter, including cancer cells, way better than gamma rays, why would we use gamma rays? Because they can get there, right? They can fire these gamma rays at you and they can go through your cells, go through your body and get to the tumor. Now, if they had a way of injecting radioactive material into a tumor, directly into a tumor, that would release alpha particles, then you can imagine how potentially at least effective that might be if they had a way of getting them directly to the tumor. The other issue though with alpha particles is that because they have such a high ability to ionize matter, yeah, they attack the cancer cells really, really well, but they also attack healthy cells really, really well too. So gamma rays seem to be the ones that tend to work the best because they have a high penetrating power and because they don't attack healthy cells quite as much. I want to describe right now the reactions that take place using equations. And I want to define a term before we do that, a term called transmutation. Transmutation is the conversion of one element to another. Now that might sound an awful lot like the definition that we gave you for radioactivity. Listen carefully. Radioactivity was the decay of a nucleus. Transmutation is the conversion of that nucleus to something else. Nuclear decay of one type or another, radioactivity, fission, fusion, nuclear decay of one type to or another leads to transmutation. It's a subtle difference there. Radioactive decay is not the conversion of an element, but the decay of an element that leads to the conversion to something else, the transmutation to something else. So transmutation is just the conversion of an element to another element that can happen by radioactivity, by fission, by fusion. We're going to talk about both of those this week. We're going to describe the transmutation of one element to another by radioactivity or by fission or fusion using a nuclear equation. And a nuclear equation is somewhat like a chemical equation, except that in a chemical equation, you're balancing elements. You got 3 carbons on the left side, you got to have 3 carbons on the right side. In a nuclear equation, that's not the case because we're transmutating one element to another. So in a nuclear equation, we're balancing something, but it's not elements. Here we're balancing protons and neutrons. Okay, let's take a peek at an example here. Number 1, it's on the back side of the sheet that I handed it to you on Friday. It says, write the nuclear equation for the transmutation of the radioactive isotope radium-226 undergoing alpha decay. If it's undergoing alpha decay, then that means an alpha particle is produced. That's the ionizing radiation that's produced. We essentially, in this question, want to see what other nucleus is produced. What is the radium turned into in addition to this ionizing radiation that we call alpha particles? So we start with radium-226. 88 protons, 226 protons and neutrons. It produces an alpha particle. You could say 42 alpha, you could say 42 He, it doesn't really matter, same thing. The alpha particle does not go on the left-hand side. We're producing an alpha particle. It's what we call part of the daughter nuclei. The parent is the radium-226. The parent is what produces the daughter. The daughter is on the right-hand side. The parent is on the left-hand side. It would be like reactants and products in a chemical reaction. What else do we produce here? What else is a product in this? Well, 4 plus 222 is 226. 2 plus 86 is 88. And if we look at a periodic table, 86 is radon, Rn. Now, I don't believe that radon-222 is stable. I believe it's still radioactive. That's going to happen a lot, where you have a decay equation that describes the transmutation of one element to the other, and it's still not stable. It could undergo what we call a decay chain, where radium turns into radon turns into something else, that turns into something else as a result of an attempt to become more stable. Always balance the atomic number, always balance the mass number. Good to go. Let's take a look at another example here. Number 2, it says, write the nuclear equation for the transmutation of lead-214 undergoing beta negative. Yep. Yep. Yeah, you would. Yeah. No, that's a good question. Do you just assume that you have one alpha particle always? For each nucleus, assume that you either have one alpha or one beta or whatever the case may be. Now, as I say, this could turn around and produce another alpha particle or a beta particle or whatever. So you might end up getting more than one alpha particle out of it, but that particular transmutation only produces one. Good question. So this one is the transmutation of radioactive isotope lead-214 undergoing beta negative decay. By the way, if they ever just say beta decay, they don't say beta negative or beta positive, just assume beta negative. So it goes beta negative decay. We're going to say it produces a negative beta particle. So it's got to be on the right-hand side versus the left. 214, 0 plus 214 gives me 214. Minus 1 plus. This is probably one of the most common mistakes made this unit. Minus 1 plus what gives me 82? 83. Okay, what do you think the mistake that people often make there is? 81. Okay, it is not 81. Okay, 1 plus 81 would be 82. Minus 1 plus 83 gives me 82. This is bismuth, I believe. If you take a look at your periodic table. Don't need to memorize those, of course, but that's why you have your periodic table there. Now listen carefully. When you have beta negative decay, there is also something called an antineutrino produced. So it doesn't come into the mix in terms of balancing things, but it does have to be there. It was observed for a number of years that we're missing something in the description. One second here, guys. Missing something in the description of a beta negative particle. A guy named Wolfgang Pauli hypothesized in 1930 that it was this tiny little particle called an antineutrino. And sure enough, since that, we found that in fact is the case. We've observed these things. Let's do one more quick one here, and then we'll wrap it up, okay? Write the nuclear equation for magnesium 23 undergoing beta plus decay. Magnesium 23 undergoing beta plus, 0 plus 1 beta particle, or you say positron if you want to call it that, plus what? 0 plus 23 gives me 23, plus 1 plus 11 gives me 12. And that's going to be, I believe it's sodium. What do you think you're going to add on here? What is it, Caitlin? Good. It's not an antineutrino, it's a neutrino. So whenever you have beta negative decay, always, whenever you have beta negative decay, it's an antineutrino. Whenever you have beta positive decay, it's a neutrino. Okay, your homework for tonight is, of course, a Millikan quiz tomorrow. And in addition to that, I'd like you to do worksheet number 24. That should go pretty quickly for you.